Unit 1, Up an Atom. You can access this video and this review on srhschem.wikispaces.com and on YouTube channel LaFell Labs. First question is about subatomic particles. So the subatomic particles that make up the atom are the proton, neutron, and electron. So the proton and neutron are both found in the nucleus. The proton has a positive charge while the neutron has a neutral charge. The electrons are orbiting the nucleus in discrete energy levels, and those have a negative charge. The table here is about isotopes. So based on the information that we have, we can fill out the rest of the table. So first, when we see an element written in isotope notation, the number on top is the mass number, and the number on bottom is the atomic number. We also might see it written out as a name, in which case the element is followed by its mass number. The atomic number is equal to the number of protons, while the mass number is the sum of protons and neutrons. So the mass number is adding up the heavy, massive parts of the atom. Protons and neutrons are very big and heavy compared to electrons, which are very, very small and almost massless by comparison. The charge is found by looking at the number of protons and the number of electrons. So the protons are positive and the electrons are negative, and based on how those numbers come out, we can determine what the charge is. I think it goes without saying, but obviously you will need a table of elements to complete these type of problems. So let's start with our first element in the table, and this is hydrogen. So we already know the name of this element is going to be hydrogen 3, and we already know that the atomic number is 1, which means that we have 1 proton. The mass number is 3. So if we know the mass number and we know the atomic number, we can figure out how many neutrons there are. So mass number is protons plus neutrons. I know that the mass number is 3. One of those is a proton, so that means that the other 2 are neutrons. To figure out the number of electrons, we need to look at the charge. So for this particular atom of hydrogen, there is 0 charge. It's neutral. So that means that I need to have an equal number of protons and electrons. You can think of it as this. 1 proton minus some number of electrons is equal to the charge, which is 0. So the only number that does that is 1. So for our next element, we have cobalt 59. So from the name cobalt, I can look that up on the periodic table and I can determine the atomic number is 27. So we just look for cobalt, whose symbol is CO, and then we know the atomic number as well as the number of protons. I also know from the name that's given that the mass number is 59. So this means that the sum of my protons and neutrons is equal to 59. So if I subtract out those 27 protons from 59, I'm going to be left with 32 neutrons. To figure out the number of electrons, we have to look at the charge. So in this case, the charge is -1. The only way that's possible is if I have one more electron than the number of protons. So if I have 27 protons with a charge of -1, I gotta have 28 electrons. So if we did the math, 27 protons minus 28 electrons gives us that -1 charge. So now I know everything that I need to know about the element, so I can go ahead and write the symbol. So the mass number 59 goes on top, atomic number 27 on bottom, and since this one has a charge, we're going to write that as superscript as -1. If we look at the next element, it looks like we don't know that much about it, but actually this gives us all the information that we need. The atomic number is 1, which means that we have 1 proton. The mass number is also 1. So the mass number is the sum of protons and neutrons, and I know I have 1 proton, so the only way that I have a mass number of 1 is if I have no neutrons. If I look at the number of electrons and the number of protons, I see that I have more protons than electrons, so this will have a positive charge. So 1 proton minus 0 electrons gives you a charge of plus 1. So I already know that this is hydrogen 1 with a mass number of 1. And whenever I make my symbol, I'm going to have a mass number of 1, an atomic number of 1, and a charge of positive 1. For my next element, I'm given that the atomic number is 27, so I already know that the number of protons is 27. I also know that the number of neutrons is 39. So if I add the 39 and the 27, that's how I get a mass number of 66. My charge is plus 1. So in order for my charge to be plus 1, I have to have one more proton than the number of electrons. So if I have 27 protons, I must have 26 electrons. 27 minus 26 is going to give me that positive 1. So I know that this is another cobalt. This is cobalt 66. So I can write out my symbol. 66 is my mass number, 27 is the atomic number, cobalt is CO, and the charge is plus 1. So for our last element, I am given that the number of protons is 28, which means that the atomic number is 28. I'm also given the mass number is 32. So I need some number that whenever I add 28 to it, it gives me 62. So 34 plus 28 gives me 62. To figure out the charge, I need to look at protons and electrons. So I have 2 more electrons than I do protons. So 28 protons minus 30 electrons gives me a charge of minus 2. I can look on the table of elements and find atomic number 28, and I see that that corresponds to nickel, so I'm going to name this element as nickel 62. When I write the symbol, 62 goes on top for my mass number, 28 is the atomic number on bottom, nickel has the symbol Ni, and the charge for this nickel is minus 2. So in this table, which of these letters represents isotopes? So isotopes are going to be atoms of the same element. So that means they have the same number of protons, the same atomic number, but they have different number of neutrons. So the mass number is different. So if we look at A and C, those are both isotopes of hydrogen, hydrogen 1 and hydrogen 3. And if we look at B and D, those are both isotopes of cobalt, cobalt 59 and cobalt 66. Which of these are going to represent cations? So cations are positively charged particles. You can remember that because the T in cation is a positive sign. So those are going to be C and D, which both have a charge of plus 1. Anions are going to be negatively charged particles, and that's going to be B and D. So those both have a negative charge. In an isotope, the number of protons, aka the atomic number, is always the same. That is correct because the number of protons is equal to the atomic number. But the number of neutrons, also known as the mass number, will vary. And that's because in order to get the mass number, I have to add protons and neutrons. So that number of neutron can change. How would we find the number of neutrons for the isotope below? Number of protons. So the top number is the mass number, which is the sum of protons and neutrons, while that bottom number is the atomic number. So if I take that mass number and I subtract out the atomic number, that's the same thing as saying if I take protons and neutrons and subtract out the protons, what I'm left with is the number of neutrons. And of course, the number of protons is exactly equal to the atomic number, which is written as Z in this particular notation. Question 6, we are looking at a bright line spectra. So bright line spectra are generated whenever elements absorb energy and then they re-emit that energy in the form of electromagnetic radiation. So that might be, in this case, visible light, which we can see with our eyes. So the way that we're going to approach this problem is we just want to match the elements that are our choices to the mixture. So I like to do this just by highlighting the lines that match up. So I see that I've got lines from strontium, that lithium lines up. There's the other lithium line. There's a couple more strontium lines, another lithium line, and the strontium line. And then the strontium line has these two bright lines over around 400 nanometers. So based on this, I can see that I've highlighted every uh, bright line for sodium and every bright line for lithium. And for cadmium, there's still ones that are missing. So this mixture contains lithium and strontium because it matches. It doesn't have cadmium because it's missing the bright lines that would match to cadmium. On the bright line spectrum above, lithium emits and absorbs light at 4 wavelengths. So using the scale provided, determine the wavelengths of those 4 emission lines to the correct precision. So if we look at this scale, it goes by 100ths. And you might be saying, well, wait a minute, it goes by 50s. But whenever we're trying to measure something with correct precision, we're always trying to guess to the next lowest place, so the next power of 10. So that 50 marker is nice to help us kind of estimate where things are, but the precision of this particular scale goes by 100ths. So that means that we know the 100ths place, we have to guess the tens place. So for this first line, again, we're going by tens. So I'm going to guess that's about 670. I can't do any better than that because I'm not even sure about that 7 in the tens place. The best I can do is 670. It looks more than 660 to me, so I said 670. Our next line is just a little bit past 600, so I'm going to estimate that to be 610. Again, I can't do any better because my scale goes by 100ths, so the best I can do is to guess that tens place. The best I can do for the next line is 500, even though I think it's a little bit before 500. But the best I can do with this scale is to guess that that's a 0 in the tens place. And then my last line here is at 460. So a little bit past the 450, I'm going to guess that that's 460. So now we need to rank those wavelengths from least to most energy. So energy runs along the electromagnetic spectrum. This includes everything from the microwaves that are used to cook your food, the radio waves that you use to make a phone call or to listen to the radio, the infrared radiation, the heat that's given off by your body, through visible light, all the way to ultraviolet light from the sun, X-rays, gamma rays. These are all forms of electromagnetic radiation. So long wavelengths like radio waves are going to be low energy, whereas really short wavelengths are going to be high energy. So I need to rank this from least energy to most. So I'm basically going to rank this from longest to shortest wavelength. So 670, 610, 500, 460 nanometers. On the bright line spectrum, why does lithium emit light at the given wavelengths? Explain in terms of electron transitions. So here I have an atom, and this is a Bohr model of the atom. So we see our nucleus in the center, and orbiting around this particular nucleus, I have one electron. And that electron is in the n equals 1 energy level. We call this the ground state. Now, it's possible that this atom, and in particular this electron, might absorb some energy. So if energy is absorbed by that electron, it's going to jump up into a higher energy level. We call this the excited state. So it has jumped up from the first energy level to the third. This arrangement is unstable. So in order to regain stability, the atom is going to need to give off, it's going to re-emit that energy in the form of electromagnetic radiation. In doing so, that electron is able to relax back down to the ground state. So that extra energy has been re-released. The energy of these transitions matches the wavelengths that we see on the bright line spectrum. Now, there are many possible transitions. This is just a very simple model of the atom. Some of those transitions might be really large, in which case the energy that is given off, those wavelengths are too high. They're above the visible spectrum and we can't see. Um, and it could also be that the amount of energy given off is really small. So that's again outside of that visible spectrum. So we don't see that either. Only certain transitions have just the right size for us to see on a bright line spectrum. So it's kind of a Goldilocks situation where the energy transition needs to match something that our eyes can detect in the visible spectrum. How does this relate to the flame test? So in the flame test, we used a flame to excite those electrons. So they jumped up in energy level. That energy would be given off by the atoms as their electrons relax down to the ground state. So our eyes we were able to detect some of those energy transitions, which fall onto the visible light section of the electromagnetic spectrum. And we are able to detect this, and we could actually use this to help us identify unknown elements by matching their colors. For the next question, convert the biggest and smallest wavelengths into meters. Write your answer in scientific notation. So our smallest wavelength was 460 nanometers. So we want to convert this into meters. So I know that I need to put nanometers on bottom, and I want to convert into meters, so that goes up top. So nano sounds like 9, and nano is 1 times 10 to the negative 9. So if I have 1 nanometer, that is 1 times 10 to the negative 9 meters. So whenever I plug that in and solve, nanometers cancels nanometers, and I get meters. Now that number is kind of ugly looking, so we're going to save ourselves a little bit of heartache here and write that in scientific notation. So I get 4.60 times 10 to the negative 7. I moved that decimal until there was only one number in front of it, and I counted the number of times that I had to move it, which was 7. And since this is a small number, I'm going to have a negative exponent. The procedure is very much the same for our 670 nanometers. Same conversion factor. This time I get a slightly different number because I started with a different number. And whenever I write this in scientific notation, I get 6.70 times 10 to the negative 7. The next problem asks us to calculate the average atomic mass of bromine. So I have one isotope of bromine which has an atomic mass of 78.92 AMU and a relative abundance of 50.69. The other major isotope of bromine has an atomic mass of 80.92 AMU and a relative abundance of 49.31%. So I color coded these isotopes because I don't want to mix up and associate the wrong percent abundance with the wrong atomic mass. So I'm just going to carry that blue and green all the way through. So here is my percent abundance. My first step is going to be to divide that by 100 so that I can write it as a decimal. So this is equivalent to moving the decimal point over 2 spaces. Just make sure that sometimes you have a percent abundance that only is in the ones place. Like if you had 5.69%, you would need to move that decimal place over 2 spaces so that you would have 0.05. But otherwise, you just need to divide by 100. And then we're going to take that decimal percent and we're going to multiply that decimal by the atomic mass. So what this is going to do is it's going to give me how much the overall mass is weighted towards the more abundant isotope. So these are the numbers that I get. My last step here is going to be to add those up. So I get this number, and I can check my work really easy because if I look on the table of elements, what I get here should match what's up there. And here you see that we're really, really close. The reason for the difference probably has to do with sig figs or with rounding. The next problem asks us to find the weighted average of the isotopes in the table. So this information is just presented a little bit differently, but we're going to do basically the same thing. First, I need to take that percent abundance and get it into a decimal percent. And then I'm going to multiply that by the atomic mass. And I'm going to do that calculation for all three of my isotopes. So I get those numbers, add everything together, and then there's my weighted average. You may notice that for my isotope A, that my number in blue is the largest of the numbers, and that's because it has the highest percent abundance. So of course we're going to see that isotope A's mass weighs into the overall mass more than the other less abundant isotopes. Question 10 is about completing the nuclear reactions and then identifying whether or not they are fission or fusion. So the main rule whenever you write nuclear reactions is that we want the top numbers to add up to the same thing on both sides of the arrow, and the bottom numbers should add up to the same thing on both sides of the arrows. So my number on top before the arrow is 226, and then after the arrow I have a 4. So I need some number that when I add 4 to it, it's going to give me 226. So that turns out to be 222. For the bottom, I have a 2. So I need some number that whenever I add 2, it's going to give me 88. So that's 86. For my next one, I have these two hydrogens. So I know that before the arrow I've got a 1 and after the arrow I've got a 2. So that missing piece has to have a 1 on bottom so that the bottoms will add up to 2. And the top piece has to be 2 because I need some number such that when I add 2, I get 4. So that number is 2. For my last one, I'm starting with uranium-235 on top. So I need some number plus 4 that equals 235. So that's going to be 231. And then for my bottom number, I have 2 and I need to add up to 92. So I need that other 90. So as far as which one is fission or fusion, fission is where a heavy nuclei breaks apart to make lighter nuclei. And fusion is where those light nuclei are fused together to make heavier ones. So if we look at the first one, we're starting with a heavy atom. The mass number is 226, and it's breaking apart, and we're releasing that alpha particle. So this is fission. In my next problem, I am taking 2 hydrogen, and that's the lightest element, taking those 2 hydrogen and fusing them together to make helium. So this is a fusion. And for my last one, I am starting with uranium, which is a heavy element, and then an alpha particle is going to break off, and I'm also going to form another element. So this one is also fission. Carbon-14 has a half-life of 5,700 years, and it decays to produce nitrogen-14. So carbon-14 is what's used with radioactive carbon dating. We know the half-life of carbon-14, so we can use that information, and based on how much carbon-14 is found in a bone or in some kind of living tissue sample, we can figure out how long ago it was since that thing died and stopped taking in more carbon-14. So if I start with 100 grams of carbon-14, how much nitrogen-14 will I have after 17,100 years? So the first thing I need to figure out is how many half-lives are there in 17,100 years. So I know that one half-life is 5,700 years. So if I divide, I know that I have 3 half-lives. So that means I need to take 100 and half it 3 times. So 100 grams of carbon-14, if I half that for one half-life, that's 50. If I half it for the second half-life, that's 25. And then one more half-life means that I have 12.5 grams of carbon-14 left. So 12.5 grams remain. What happened to the rest of the carbon? That carbon-14 was converted into a stable product, which is nitrogen-14. So if I have 12.5 grams of carbon-14 left, that means the rest of it, the other 87.5 grams, have been formed into nitrogen-14. For the next problem, a sample contains 25 grams of carbon-14 and 175 grams of nitrogen-14. So how many half-lives has it undergone? So the total that I started with was 25 plus 75, which is 200 grams. So this sample started as 200 grams of carbon-14. So how many half-lives does it take to go from 200 grams down to 25 grams? So half of 200 is 100, half of 100 is 50, and half of 50 is 25. So that means that it took 3 half-lives. 25 grams of carbon-14 are left, and the other 175 have decayed into stable nitrogen-14. So the sample has undergone 3 half-lives. Explain how nuclear reactions are used to generate electricity in a nuclear power plant. So a nuclear power plant works very similarly to a coal power plant. The only difference is how does it produce heat? So within the reactor, I have fuel rods which contain a fissionable element. And as that reaction happens, it gives off lots and lots of heat. That heat is then used to convert water, liquid water, into steam. And that steam will power steam turbines and generate electricity. That steam can then be recondensed and be used again and go through the process to generate more electricity. What's really nice about this is that it doesn't depend on something like the wind or the sun. Um, and we can control this reaction using the control rods. So we insert those further. It absorbs some of those neutrons and slows down the reaction. That way we don't waste our fuel. But of course, the problem here, this does generate a lot of electricity, but there is a danger of a meltdown. So the reactor produces more heat than the water can absorb, and the reactor actually fuses with the uranium inside. We also have issues of radioactive waste. Some of those isotopes have half-lives of tens of thousands of years, so it means that there'll always be a problem in our environment. But pros or cons aside, America gets around 20% of its electricity from nuclear power.